What's going on, everybody? In today's video, we're going to take a look at how we can use power functions and use that to model some of the more typical problems we see on IB exams or AP exams, how we can manipulate those, and how also we can extract some really important information out of the graph. Let's go ahead and dive right in. All right, so we have a can of cat food that is going to be cylindrical. It's a can. We're given the volume is 200 cubic centimeters. We're given that the radius is r and the height is h. Go figure. And then, of course, this should be either in your memory or in your formula booklets, the volume of a cylinder formula, as well as the surface area of a cylinder. I'm sorry, the area for the curved part of the surface. Now, let's explain why pi r squared h equals 200. Well, that's simple enough because I'm given that the volume is 200 cubic centimeters, and then what is the volume formula? Pi r squared h. So if I just replace this in for v right there, I'm going to get, indeed, pi r squared h is equal to 200. I just replaced the volume with the formula, pi r squared h. Now, let's rearrange the equation from part A to make h the subject. Remember, when you say make h the subject, it means you want h equals blah, blah, blah. So let's rearrange it so that h is the subject. All that means we're going to need to do is just divide by each side by pi r squared. And we'll go ahead and have h all by ourselves. So they'll end up with 200 all over pi r squared. Cool. Now let's find an expression for the total surface area of the can. Remember that surface area is everything that you can basically touch, wrap around, paint, however you want to visualize it. But if you think about it, when I have a cylinder, I can kind of touch everything that goes around the cylinder, kind of almost like this this microphone here, everything that goes around as well as what's on top and as well as what's on the bottom. Now, so that means I have the area of all of this curved surface here, which I'm given as 2 pi r h, as well as the area of a circle up here and the area of a circle down here. So I'm going to have my surface area is equal to my 2 pi r h, and I need to add on to that the area of here, pi r squared, and I have another pi r squared down here. So that gives me 2 pi r squared. So that is going to be my total surface area of the can in terms of the formula. So now this is where things get perhaps a little bit more complicated, but again, it's a very typical solution approach to these types of problems, is that what we want to do now is we want to be able to graph this. And in order to do that, we want to put this equation in terms of one variable. What variable do we want that to be? In this case, we want it to be r. So as I'm told to substitute your expression for h from part B, this right here, into here. Because what that will do is that if I plug in this for h right here, I will have only r, and r in my equation. So I'm only going to have this equation in terms of r. I have one variable. I'm not going to have any issues graphing it. So let's go ahead and do that. So let's go ahead and say that, okay, my surface area is going to be equal to 2 pi r, and then I'm going to have 200 all over pi r squared. I just substituted that, plus 2 pi r squared. So now let's do a little bit of simplifying. I know that I can go ahead and kind of cross cancel. I have a pi here, r there, one of the r's there. So what that's going to give me is a surface area of 400 all over r plus 2 pi r squared. And in the problem, they were kind enough to say make sure it checks out with that, in which case it absolutely does. Excellent. So now what I want to do is I want to use scale for the axes, plot the equation, and then find the minimum surface area of the can and the value of r for which this occurs. I want to minimize the surface area. A lot of application to that would be like if you are painting it or if you are applying a logo, you might want to use the least amount of paper possible. So that's a really good way to know, it's like, hey, for what value that radius, for how big I kind of make the circles or how wide I make the cylinder, I can now dictate how much I can spend on the paint or on the logo or on the paper or whatever it happens to be. So when you're looking at the graph, what this is telling you is that, okay, my input is the radius on the x-axis, my output is the area on the y-axis. So if I want to find the minimum surface area possible in what radius that's going to put out, I want to find this minimum point down here. So when I go ahead and I analyze this graph and then I find the minimum, I'm going to get a value of 3.17 and 1.89. So what that means in terms of our x and y coordinates is that when I have a radius of 3.17 centimeters, I'm going to have a minimum possible surface area of 189 square centimeters. Okay, so again, I am looking for the minimum surface area. That means I'm looking for the minimum on this y axis, and that reaches this point down here. So when I have a radius of 3.17 centimeters, I have an output of a surface area that is a minimum of 189 square centimeters. Okay. So I hope that helps you see how we can use what we've learned about power functions, as well as some things that we've learned in previous years in algebra classes to solve more complicated problems. In this case, what we did is we took surface area and volume, and then we rearranged a couple things. We plugged one variable in for another, so that way we had an equation in terms of one variable. We plotted it. We found a minimum, all within the context of our problem. Okay, I hope that helps, and I'll see you all in the next video.